So welcome to today's seminar on feasible interpolation for algebraic proof systems with Tuomas Hakoniemi from UPC in Barcelona. So Tuomas has done a lot of work on different aspects of algebraic and semi-algebraic proof systems, and he will tell us about some of this work today. Please, Tuomas, the floor is yours.
Thank you. So, yes, the topic is on feasible interpolation for algebraic proof systems. So let's start with feasible interpolation. So just a quick introduction so that we are on the same page. What we mean by that term. So basically, feasible interpolation it's a quite general framework introduced by Krajicek in the late 90s for basically extracting computational content out of proofs. And originally it was conceived as a method for reducing length of proofs lower bounds to lower bounds in other computational models. So the basic idea there is that given this kind of an unsatisfiable conjunction that shares where the two conjuncts share some sequence z of common variables, but they have their distinct variables also. Interpolating function is a function that basically given an assignment to the z variables tells whether left or right hand side is unsatisfiable. Okay. One side is if the original conjunction is unsatisfiable, and the idea behind feasible interpolation is to somehow translate this a given refutation to a somehow feasible algorithm computing the interpolating function for the conjunction. So the exact notion of a feasibility depends on really on the problem at hand, and originally and most commonly it was used to mean basically feasible interpolation with respect to polycized Boolean circuits. So whether one can transform the proof into Boolean circuits that compute an interpolating function that's only polynomial larger than the given proof, basically. Okay. So originally it was the first lower bounds obtained by this was what Krajicek in the original paper for resolution from lower bounds on monotone Boolean circuits. So showing that if one has a resolution refutation of a conjunction satisfying some monotonicity conditions, then one can transform that into monotone Boolean circuits that compute the interpolating function and then obtain resolution lower bounds from lower bounds on monotone Boolean circuits. This was extended in the same year for cutting planes from lower bounds from monotone real circuits. And on the negative side of things, a year later, Krajicek and Pudlak showed that a strong proof system, the extended Frege, cannot admit feasible interpolation unless some quite strong cryptographic assumption breaks. So here basically how this proof works is by showing that extended Frege is strong enough to carry out the necessary arithmetic and prove their correctness within the proof system to prove basically the correctness of the RSA algorithm, and then prove a statement of the form that the original message has either 0 or 1 as the first bit, and if one would have feasible interpolation, one could crack the RSA basically. And this was extended to slightly weaker systems using a slightly weaker cryptographic assumption. Okay, so let's next talk about the two proof systems I'm gonna look at. They are polynomial calculus and sums-of-squares. So a polynomial calculus is a polynomial proof system based on schematic inference rules, so that proofs are actually like DAX or trees. And so you have two different rules basically. So lifting by a variable, a previous polynomial obtained in a sequence, or then or linear combination of previous polynomials. And I should say here somewhere that the PC refutation is a proof of 1 equals to 0. Okay. Sums-of-squares proofs, on the other hand, is a completely static proof system. Let's say just one single equation that's basically, but rather strong proof system. So proof of sums-of-squares proof is just a sum of squares plus lifts of the given axioms and the Boolean axioms. And sums-of-squares refutation is a proof of non-negativity of -1 from the given axioms. Okay, so I was running to get to that to our results basically. So what's the form of feasible interpolation we prove for these two systems? It's as follows. So not only is the interpolating function computable in polynomial time in the size of the given refutation, but one can actually find one of the conjuncts for both of these systems. So here, in general, we're given two sets of polynomial equality constraints that I can share some common variables and then have their own distinct sets of variables. Some refutation of their union. So this is really like a conjunction, and an assignment to the z variables. Then in polynomial time, we can output either a refutation of P where A is applied to the z variables, or a refutation of Q when A is applied to the z variables. Okay. So just a few words on the overview of the proof. So what's the general idea here? So the proof itself is actually quite logical in character, in that we first prove the existence of a suitable small refutation of one of the conjuncts, and then give in both cases like a simple proof search algorithm for the conjuncts. And the first step of proving the existence of these refutations involves a semantic argument. And this is using what I call semantics for resource-bounded refutations. So basically, using some kind of a mathematical object that captures a well-behaved class of refutations somehow. So the class that we are after should satisfy basically two criteria. So we need to be able to characterize the refutations inside the class somehow with a well-behaved sound and complete semantics, so that we can actually work with the semantic tools. And on the other hand, the class should be small enough so that we can actually just brute force the search within the class efficiently. And the basic idea here that, so where do we get the necessary information for the, so what is the class that we need to consider? So within which class we are looking for the refutation of this PXA or QYA? Well, that information comes from the given refutation of this conjunction. So this given refutation contains all the necessary information so that we can define these classes and show that either one of the conjuncts must have a refutations within their respective class. Okay. So before going to more details, does anybody have any questions at this point?
I am trying to parse the results. So the interpolation results you talked about before for cutting planes and for resolution, there we start with a refutation.
Yes.
And the interpolation process produces a circuit.
Yes.
The fact that you could also, like, you can always just, I mean, if you had the refutation of the whole formula and you hit that refutation with a restriction, then it remains a refutation. So that, I guess, you could also do, but somehow it's important that we build these circuits. But here we are extracting like the restricted, I guess, yeah, so I'm trying to understand here we're restricting a refutation, and like, why don't we just get that from hitting the original refutation with a restriction? So I'm missing something, I think.
So so okay, so the restriction is so okay, you have this refutation of this conjunction.
Yes.
First, you'd hit it with this restriction to the z variables, and you'd have that would be a refutation of this union this, right?
Yeah.
Okay, then you'd hit it with some restrictions to say y variables. But then, of course, if you have a restriction that then kills all these polynomials here, sets them all to 0, then that solves really the problem.
Yes.
Right. But you might not have that. So if both of these sets are unsatisfiable, so these are so then you don't have this this restriction that sets one of the sides to 0, so that you get the refutation of the other side.
Mm-hmm. So you're saying if I chose a restriction that actually falsifies both of them, then you're still able to extract the refutation of just one side. Kind of. Is that one way of viewing it?
So so what I'm saying is that if both of these sides are unsatisfiable,
yeah, after applying the restriction,
after applying this a to the z, then hitting this with some y, some restriction to the y's does not give a refutation of this other side necessarily, because you are left with non-zero constant polynomials. So well, so if of course if you have this if after assigning these a variables, one of these is satisfiable, so that you have some restriction that sets all of these to 0, then that gives you a refutation of the other side. But if both of these are unsatisfiable, then this kind of a attack doesn't work.
Yeah. Right. Yes. Okay.
Okay.
May I ask?
Yes.
Does this work for any arbitrary restriction? Assignment A. Is it arbitrary?
So okay.
Not. Oh.
For some squares, I maybe galloped my way through this, but for some squares we are looking at 0, 1 values, so Boolean variables. And for polynomial calculus, we actually obtain this result only for over finite fields. So then there it still applies for any assignment in the finite field. But
okay.
So for polynomial calculus, it's any assignment in a finite field. For some squares, it's 0, 1 assignments.
Okay. Thank you.
Okay. Okay. So maybe we continue then. Okay. So for polynomial calculus, so what's the class of proofs that we look at? It as what I call proofs over a set of monomials. So we define next this class of proofs and give the appropriate semantic characterization for such proofs. And this semantic counterpart it's a variation of the reduction operators introduced by Rasberov. Let's say basically the standard tool to prove polynomial calculus lower bounds. But actually, these kinds of objects also can be used to characterize the proofs, so that you have basically completeness property also. And the proof search algorithm here is just is on the other hand a modification of the one given by Legg, Edmonds, and Imbacliad. So basically, these are just the tools used are minor modifications of existing tools, but putting them into a right context, basically. So we say that a polynomial calculus proof is over a set S of monomials. If any polynomial in the proof is a polynomial using only monomials from S hat, which is all the monomials in S lifted by some variables, and actually I should have union S here, so S hat should contain S also. Okay, and this inference step of lifting by a variable is only applied when the antecedent is a polynomial containing only monomials from the original set S. So this is a generalization of a PC proof of degree D. So basically, a PC proof of degree D is just a PC proof over a set of all monomials of degree D minus 1. Okay.
Tuomas, a quick question. Do you assume that the initial polynomials are in the set S, or they might be arbitrary?
Yes, they should be in the set S. Yes.
All the monomials are in the set S.
Yes.
They should be in the set S.
Yes. Okay. And the semantic counterpart is the reduction operator. So we say that the reduction operator is a linear function from this f s hat to itself that satisfies the following. So maps the constant polynomial 1 to 1, all the axioms to the 0, is idempotent, and then satisfies this. I'm always trying to find words to describe what this is, but well, this property. I don't know. Does anybody have a good name for this?
What would we say that we do? Somehow it's some kind of commutation operator with multiplication, except that it's not commutativity. It's something else, I guess.
Yeah.
It distributes over multiplication, or I don't know.
Yes.
I have to learn more fancy math terminology. I'm a computer scientist.
It's a remainder, no, or something, no?
It is. It works exactly as the remainder operator would. I mean,
yes.
So, any modulus operator, modulo and ideal would work in this way. Yeah.
Yeah. Okay. So indeed, these kinds of operators can be then used to characterize the existence of a PC refutation over the set S of monomials. So we have the following soundness and completeness: that there's no refutation if and only if there's a reduction operator. So the soundness part, so if there's a reduction operator there, then there's no refutation, is quite easy. It's just a induction on the proof, basically, starting from the leaves down to the root, and in the end you get a contradiction. So basically showing that every element in the proof gets the value 0. So in the end you get a contradiction with the first item here. Okay. And the completeness on the other hand is just like is a remainder operator, basically. I was planning to go through the details in the second half of this talk. Okay.
So basically what you're saying is that suppose that we have a set of polynomials that are satisfying, then you'll just let the reduction operator be reduction modulo the ideal generated by those polynomials.
Yes, but also yes, if they are satisfiable, but if they are unsatisfiable, but there's no refutation, then you have to work basically not modulo the ideal, but modulo this basically subspace of anything provable with over S from those axioms.
Oh,
Okay.
we're not assumable 0-1-ness here, are we?
No.
Because I guess if you also have the Boolean axioms, then anything unsatisfiable is also refutable. But your setting is much more general, you say.
Yes, for polynomial calculus, it's so this semantic part, this works completely generally for any set Q, basically.
Okay, makes sense.
Okay. Yes, and for any field. Okay. So using this characterization, we can prove what I call the feasible disjunction property of polynomial calculus. So suppose we have some refutation of now two sets of polynomials that do not share any common variables, and the refutation only uses monomials from a set S. Okay, so this is important. So we get this information about which set of monomials to use the given refutation. So then we can show that then there is a refutation of either the left-hand side over the projection of this S to the X variables. So what I mean here is by the projection is, so these are monomials that contain both the X and Y variables. So projection of a monomial to the X variables is just the product of all the X variables appearing in the monomial, just disregarding the Y variables. Okay. Or then we have a refutation of the right-hand side over the projection of the Y variables. Okay. And the proof sketch is quite simple. So supposing there was a contradiction that neither one of these refutations exists, then by completeness, there are these reduction operators for both of these sets over Sx and Sy respectively. And then we combine these to a third linear function from this set S prime. That's just the products of all these monomials from the hatchet versions of these projections, basically, and define this basically using Rx and Ry as components here. And then we can prove that this R has the following properties. So you map constant polynomial 1 to 1, you map all the axioms to 0, and then you have this commutativity kind of property. So again, existence of such R is in contradiction with the assumption that only monomials from the set S appear in the refutation. So again, by induction from the leaves of the proof down to the root, showing that any line on the proof gets the value 0, against this first property. Okay. So finally, so now at this point we have shown that there's a refutation of this Pxa over some small set or Qya over some other small set. So then we can just search within those sets for the proofs. So this is just a simple modification of the proof search algorithm of Clegg, Edmonds, and Impagliazzo. So for any fixed finite field, one can find the refutation of some set Q over some set S of monomials in time polynomial in the size of the set of monomials, the size of the given axioms and the number of variables. But unfortunately, for rationals or reals, there's a potential for serious coefficient bloat that itself will basically work against the running time. So basically, even for rationals or reals, one can search for the proof in polynomial number of basic operations, so to say, but your coefficients might blow up so that you lose polynomial runtime. And this is not only a potential, but there's a counterexample. So this is even for polynomial calculus resolution. So even in the Boolean realm. So you have a set of unsatisfiable constraints that have a degree 2 PCR refutations over rationals, and thus also with polynomial many monomials. But any refutation either has exceedingly large coefficients, exponential number of monomials, or is of exponential height. So in any case, you cannot find the refutation in time polynomial in the size of the set of the monomials, basically. Okay, so we should somehow take into account also the size of the coefficients here, but there's future work. Okay, so in the end we get this feasible interpolation for polynomial calculus for any finite field, as stated also previously. So we can find a refutation of one of the conjuncts. Okay. So before going to sums of squares, does anybody have questions?
Can you go back a second to the counterexample, a couple of slides ago?
Yes.
Yes. So okay. Is this Q1 explicit? Sorry, I got.
Yes. Yes. Yes.
You said it probably.
Yeah, I can come back to this in the second half.
The second part. Okay.
More details. Yes.
And then the second bullet point is that it's either you don't know which of these is the case. The refutation contains larger coefficient or a lot of monomials or something, or is it?
Well, this so you have at least one refutation that's of degree 2 and has only has only polynomially many monomials and whose height is very small also. Well, that refutation must have exceedingly large coefficients then. But it would be maybe interesting to see the refutations that basically fail the other two.
Thanks.
Okay. Okay, so sums of squares we have just the same basic idea. So introduce a suitable notion of a SOS proofs that we can use to prove our theorem. So again, a notion of a SOS proof over a set of monomials, and given appropriate semantic counterpart for such class of proofs. So this is again a variety of pseudo expectations. Okay, and then show that this within this class one can formalize the search as a semi-definite program whose feasibility can be checked in polynomial time. So for this, we not only need that the size of the semi-definite program is small, but we need to be careful that we have also a bound for the initial ellipse, so that we know that we don't need to start from too far away, and that's why we have to look at SO. So here we need to take into account these coefficients really, so that the initial ellipse can be bounded to small enough. Okay, so now we say that then SOS proof of non-negativity of P from Q is over a set S of monomials. So here the S should contain all the monomials in Q, all the variables, both the basic variables and their twins, and the empty monomial one. So we say a proof over S is an equality of the form that P equals some sum-of-squares, and then lifts of the Q axioms by some polynomial using all the monomials from the set S, and the lifts of these complementarity axioms with lifts using only monomials from the set S. And this equality is modular multilinearization. So here we need to handle separately the two forms of Boolean axioms. So this complementarity axiom, we need to be careful about its lifts, but for the x squared minus x variables axioms, we don't need to be that careful. So the basic reason for this is that if two polynomials are equal modular multilinearization, there's a certificate for this that is whose size is relative to the size of the two polynomials. But this does not need to be the case for equality modulo the Boolean ideal. So having all of these also there. So that's why we need to basically explicitly bound the lifts of these complementarity axioms also. Okay. So, and we say that
so in principle, this equality modulo multilinearization means that the usual Boolean axiom, if you want to write it explicitly, they could have polynomials multiplying them not from the set R of S or something like
yes,
that?
Yes. Yes.
So you allow that?
Yes, okay. I allow that, but for the complementarity axiom, I need to restrict the lifts.
I see. Okay.
Okay.
Thanks.
So, and we say that this proof above is R-bounded. So here comes the bound that we need for to basically shrink the initial ellipsoid. If the coefficients in these lifts of the axioms are bounded by R in absolute value, we do not bound the lifts of the do not bound the coefficients in these squares a priori, but it's a lemma to show that from these bounds follow also bounds for these coefficients. But it makes our life easier with the semantic proofs when we do not bound these initially. Okay. So the semantic counterpart here is what I call epsilon pseudo expectations. So it's like a classic pseudo expectation. It's a linear functional that satisfies the following conditions. So it maps constant polynomial 1 to the value 1, any square to a non-negative value, respects the equality modulo multilinearization, and then maps the lifts of the axioms and the complementarity axioms epsilon close to 0. So the lifts by a monomial in S. Okay. And for these kinds of objects, we have the following soundness and completeness.
Wait,
lemma.
this seems like a key technical novelty. This is some kind of, the pseudo expectation is saying that the original axioms are like almost true. Is that what you're saying? I mean, normally we would want them to be 0, would we?
Yes, but this kind of a pseudo expectation works against this these bounded proofs. So basically thinking that if you have a very small epsilon, you need very large coefficients to fool it, basically. So that's the idea.
Okay.
Okay. And this is basically the soundness. So if there's a epsilon pseudo expectation for this set over S, then there's no R-bounded SOS refutations for any R less than this value. So this is just chosen so that basically applying this pseudo expectation to a refutation, that R-bounded refutation for R less than this would give a trivial contradiction of -1 is strictly less than -1. Okay. And on the other hand, we also can, so we also have this completeness. So if there is no R-bounded SOS refutations, then we have a semantic certificate for such thing. Okay. And now the feasible disjunction property goes basically the same. Here we just need to carry along these bounds on the coefficients also. So given a refutations of this conjunction, and set S of all explicit monomials in the refutation. So here, this is a so what I mean by explicit monomials is if I write this refutation explicitly, really with all even the Boolean axioms and their explicit lifts, then the explicit monomials are all the monomials in the axioms, in the lifts, and inside the squares, basically in the sum-squares part. Okay. So with this set and this given bound, we can define another bound and show that there's this R prime bounded SOS refutations of Px over Sx, or R prime bounded SOS refutations of Qy over Sy. Okay, and the proof is really the same idea. So supposing towards a contradiction that there's no such refutations, then you have this 1 over R prime pseudo expectations. And then you can combine these to a linear functional from R S squared to in the basically the obvious way, and show that it has the following properties. Again, mapping 1 to 1, all squares to non-negative values. These lifts, these explicit lifts that appear in the given refutation of these Boolean axioms to 0. So this does not necessarily respect the whole equality model of multilinearization, but it maps all the lifts that actually appear in the given refutation to 0. Okay, and this is an important little detail here. And then maps the complementarity axioms and the given axioms to 1 over R prime close to 0. And again, applying this E to the given refutation, you get a trivial contradiction. Okay. So the proof search here, as I stated, can be carried out by a ellipsoid algorithm. And for our purposes, the ellipsoid algorithm can be used to solve the following computational problem. So given a set Q of linear and semi-definite constraints, some constants big R and small r, with the promise that if there is a feasible solution, it is inside the ball of radius, this big R. So this is the initial ellipsoid, and basically the starting point. And if the feasible region is non-empty, then it contains a small ball of radius r. So this is the stopping condition. Basically, if you come across an ellipsoid whose volume is less than the ball of radius small r, then you know to stop. So with these promises, the ellipsoid algorithm can find a feasible solution for the constraints in time polynomial in the encoding of the constraints and logarithm of r and logarithm of 1 over r, small r. Okay. So the proof search for R-bounded SOS refutations then can be carried out in time polynomial in the size of the given set, the encoding, and the logarithm of the given bound R. Okay, so there are still 2 obstacles relating to these promises, basically. So we have, okay, I have big R in two meanings here, but the big R in the promise of the ellipsoid algorithm. So we have this bound for the coefficients in the lifts of the axioms, but we still need to bound the number of squares and the coefficients in the squares. Okay, so that we get a small enough initial ellipsoid to start with. And on the other hand, the natural semi-definite program for proofs over S is not full dimensional, as it contains lots of basically equality constraints. But there's a way around this, basically by fuzzying the constraints and obtaining a kind of an approximate SOS proof that then can be fixed to a proof up to an additive error. Okay. And so again, combining the feasible disjunction property and this proof search, we get the feasible interpolation as stated. Okay. So conclusions before the break. So first of all, these results do not yield any new lower bounds, but I see them as giving kind of a new information about the relative strengths of these proof systems, basically pulling them way closer to say resolution than the strong proof systems. And just want to mention that a similar proof also gives feasible interpolation for Shirley-Adams, but that would be maybe too much of a repetition to give the details here. Okay. Thirdly, we know that sums-of-squares cannot admit monotone feasible interpolation, as it has small proofs of the clique coloring formulas. But it's still open whether Polynomial Calculus or Shirley-Adams would admit monotone feasible interpolation. And finally, this question that I find quite interesting is whether these kinds of semantic arguments could be used to extend to prove a feasible disjunction property even for stronger systems. So even for systems that we believe not to possess feasible interpolation. So if one could prove really the existence of a somehow small proof using a semantic argument, even if one doesn't have this proof search algorithm to go with it, basically. Okay, so I think I'm done for the first half at this point. Thank you. Any questions?
Thomas, thank you very much for this interesting talk. I'm wondering, you already mentioned that Frege and extended Frege don't have feasible interpolation unless some cryptographic assumptions break.
Yes.
Do you have other proof systems in mind where this is believed to be the same? That could be attacked, maybe? Other proofs apart from Frege and extended Frege? Stronger ones?
To prove the... So, I'm sorry. So, can you repeat the question? So, so what? Yes.
Can you go back to the last slide, please?
Okay.
So you said feasible. You're wondering whether feasible disjunction properties for stronger proof systems is possible, even though they are not believed to possess this. And you,
yes.
In the beginning, you mentioned Frege and extended Frege.
Yes.
They are believed because of some cryptographic assumption.
Yes.
And are there other proof systems stronger?
Stronger that?
Well, I think so, such as proof systems that is in between Frege and extended Frege, maybe BC or RAD or something. Maybe you're not familiar with that one.
Other systems that do not, that we have some results about the not having feasible interpolation. Is that the question? Or
no, I'm wondering whether there are other proof systems, stronger proof systems, not Frege and extended Frege, that can be where this is possible.
Well, that have feasible interpolation.
Yeah, exactly.
Feasible interpolation. Not quite sure. What is the? Does somebody know what could be considered the strongest system?
Yeah,
I don't know.
Okay, you don't have any idea of a stronger system.
Stronger system,
but not necessarily extended Frege.
To have a feasible interpolation.
Yeah.
No.
So there are some candidates, but it's not very clear whether they are in between. They're believed to be in between. Block clauses in Boolean algebra, for instance. Okay, that was my question.
Okay.
You mean only these extended Frege and Frege, where you want to maybe?
So where I would like to take this feasible disjunction. So okay. So this. So okay, a long answer would be that okay. So what works for this algebraic proof systems here is that you have this notion of a proof over a set of monomials, and you have a very natural way to split the information on the given refutation, basically, so that you have this, you're given this proof that contains only monomials from some set S. You have a very natural way to split this to the X part and the Y part. Okay.
I see.
Okay, so this is why this works here. For the stronger systems, this is, I guess, where you might have problems. So let's even if we have say Frege proof, and say we have a notion of a Frege proof within some set of formulas. For this, we can give some quite nice behaved semantic characterization, but it is not at all clear how to split this to the two components, basically, because you have arbitrary logical formulas, that have maybe have a jumbled mess of the x and y variables there. So it's not clear how to say that what is the important information there for the two parts, basically. But maybe the interesting systems would be strong systems that only use clauses, like the DRAD or some of these kinds of systems. So for clauses, it's like clear how to separate these to the X pile and to the Y pile, the information in the given refutation, clause by clause, basically. But then the question comes, how what kind of a semantic characterizations can we give for these kinds of proof systems then? Okay, does this answers your question?
Absolutely, very interesting. Thank you.
Any other questions to Tuomas? So then I think I was a bit too slow in my reaction. So let me now then add the applause on behalf of everybody listening. And thank you for the seminar, the first half of the seminar. So now I suggest we take a 10-minute break. And we can then reconvene at, let's say, 18 minutes past the hour. But now we're having a short break.
Okay.
So we're back after the break, and Tuomas is going to tell us a bit, maybe some more of the technical stuff. It's over to you, Tuomas, again, please.
Thank you. Full screen. Okay. So I was thinking of in the technical section going through in details these semantic proofs, and because this is where I feel is the novel contribution of this work, and just quickly touch on on a bit more details on the proof search itself.
And
okay.
And is it correct again to just, when we're talking about polynomial calculus, that an important point that I missed before is that you have any polynomials now,
yes,
and you're deriving from them 0 equals 1, but we don't necessarily have these Boolean axioms or anything.
Yeah. Yes.
It's just a set of polynomials for which polynomial calculus we have a set of polynomials, and we are in a field so that happily things worked out.
Yes.
Okay.
Okay. Yes. Okay. So just a reminder, what we call a reduction operator is a linear function satisfying these four properties. Okay. And I claim that there's this kind of a soundness and completeness theorem for such objects in the first half. Okay, so the soundness, so from a reduction operators to the non-existence of a refutation, that's a simple inductive argument on the structure of the proof. but let's see the more details on the completeness. So from the assumption that there's no refutation, how to construct such a function. And this is something I think I forgot to mention, but this third item here is not necessarily, it's not necessary for the soundness, but this completeness argument gives a function that satisfies also this. And moreover, this is needed actually in the feasible disjunction property.
And again, we're not discussing whether Q is unsatisfiable or not. We're discussing the syntactic question of whether there is a polynomial calculus refutation. So even we could be in a setting where Q is unsatisfiable, but there was no PC refutation.
Yes.
And even for such a Q, you now need to find this operator R.
Yes.
And then it's clear somehow that you can't, then I guess you can't just reduce, well, or maybe you can, I don't know. It's not obvious then when you can reduce modulo the ideal, right? Because
yes.
it's not clear to me what the ideal is.
Yeah, we don't have an ideal. We have I think some have called it a pseudo ideal. But it's not a pseudo ideal up to some degree, but it's a somehow pseudo ideal with respect to this given set of monomials.
Okay.
Okay. So the basic construction starts with just fixing a sum total ordering on this S hat. So this was the S together with all the lifts of the elements of S by a variable. Okay. So, and we want this total order to satisfy the following. So we want this empty monomial to be the least element of the with respect to this ordering, and we want anything in S to be before the anything in S hat that is not in S. Okay. And just some terminology, we say that a leading term of a polynomial is the highest order term appearing in P with respect to this ordering. Okay. And we say that this term T is reducible modulo Q if there is some polynomial that is provable from Q over S that whose leading term is T. And otherwise the term is S irreducible. Okay. So
technically speaking, I guess a monomial X and its lift could both be in S hat, right? So do you, I mean, the question is, do you always want M to be smaller than X times M or not necessarily?
Yeah, not necessarily if X times M is also in S.
Okay.
Okay. So just what is sufficient is that if I have some M prime that is in S hat but not in S, that comes after everything in S. Okay. Okay. And the important fact about this irreducible terms is that you have a unique decomposition of any polynomial into a provable and S irreducible part. So you have some Q such that this Q has a proof, PC proof from Q over S, and plus some R that is sum of S irreducible terms. Okay, and moreover, this leading term of P is always at least as large as any term in this R. So you never need to add here basically a terms that are above this P is leading term. And this is also a very important property that we use. Okay. So the proof is just a construction by construction. So we construct sequences of polynomials so that P is always Pi plus Qi plus Ri. And at each step, Qi's are provable, Ri's are sums of irreducible terms. And at some point, we reach a situation where pk is 0, and then we have this at least one such decomposition of p into an provable and irreducible part. Okay, so we start with p1 being p and q1 and r1 being 0, and at each step we look at the leading term of the previous p. Okay, if it is reducible as witnessed by some q that's provable, then we take we subtract that from we get the pi plus 1 by subtracting this q from the pi, adding the qi plus 1 from by adding this q to qi, and ri plus 1 is the same. If on the other hand it's irreducible, then we subtract it again from pi, leave the qi as it is, and just add it to the sum of irreducible terms. Okay, and now at some point this pk is 0 because you are always taking away the leading term basically from the polynomial. And by construction, these qi and ri satisfy the conditions we ask from them. And uniqueness proof is then standard. So supposing that you'd have two different decompositions, then you have that R1 minus R2 is provable. But this R1 minus R2 is a sum of irreducible terms. So if it's provable, it must be the empty sum of irreducible terms. So it's 0. So R1 is equal to R2, and hence also Q1 is equal to Q2. Okay. So now if we look at this function that maps any polynomial to this unique sum of irreducible terms that appears in the decomposition, this mapping has these properties that if there is no refutation, then it maps 1 to 1. It maps every axiom to 0. It's a linear function. It has this idempotency property and this some kind of a commutativity property. Okay. Okay. So
and when you're going to prove it. Okay. Yes. Mm-hmm.
Okay. So again, if there's no refutation of Q over S, then 1 is S irreducible modulo Q. And this is here it is important that 1 is really the least element according to the ordering, so that it is actually S irreducible modulo Q. Well, on the other hand, of course, we have that 0 is provable. Okay. And so we have that 1 is equal to 0 plus 1. Well, this is a 1 decomposition of 1 into a provable and irreducible part. hence by the uniqueness of the decomposition we have that it maps 1 to 1. Okay. Again, so it maps every q to 0 because, okay, of course we have 0 as an empty sum of as irreducible terms. And trivially, q itself is provable from q. Okay. And we have this decomposition of q into a provable and irreducible part. And so by the uniqueness of the decomposition, it maps every axiom to 0. Okay. So then linearity. So of course we have that p minus this rs of p and q minus rs of q are provable. Okay, by definition. Hence we have also that this is p plus q minus rsp plus rsq is provable. But now this rsp plus rsq is a sum of irreducible terms. And thus, again, by uniqueness of decomposition, we get this, that rs of p plus q is the same as rsp plus rsq. And similarly, we can prove that. So that is, it's linear. Okay. And idempotency follows similarly. So we have both p minus rsp is provable and rsp minus rs of rsp are provable by definition. And so we also have that p minus rs of rsp is provable. And so by the uniqueness again, we get the idempotency. And here is where we actually need then the last item is where we need this, that any elements of S comes before before any element in S hat that's not in S. So assuming that we have some monomial M in that's a monomial in S, of course we have again M minus Rs of M is provable. And now each term of this Rs of M by the moreover part of the decomposition lemma basically comes before M in the ordering. So their monomial is always in S because they come before M that's in S, and everything that would be in S hat but not in S comes after M. So any monomial appearing in this S of M must be in S. So okay, now we have a term that's provable that's contains only monomials from the set S. So we can lift it by x and have that x of M minus x times Rs of M is provable. And again, if this is provable, then it follows that basically they're applying this Rs operator to both terms here, you get the same values. Okay. So we have shown that if there is no refutation of Q over S, then this operator has all the properties that we asked from a reduction operator. And thus we have completeness. Okay. Any questions about this?
I think I'm good. It's somehow quite similar to these games you play with the R operator when you prove polynomial calculus lower bound, except that there you also care a lot about the degree.
Yes.
This is somehow fairly similar in flavor, but here we're degree unbounded. It's interesting.
Yes, but it's still a slight generalization of the degree bounded case. So this refutation over some fixed set S.
Yeah.
So it's So it has a very similar flavor. Yes. Okay. So okay. So let's see. Also quickly the details omitted in the first part about the disjunction property. So these results, after finding really the correct class of proofs to consider, this almost come trivial, these especially these disjunction property proofs. But let's see. So okay, so we have constructed this R from the assumption that there's no refutations of either side, and we want to show that this R has these properties, that it maps 1-to-1 all the axioms to 0, and then has this commutativity property. So the first one is simple. Because both components map 1-to-1, then this R must map also 1-to-1. Okay. And as if you have an axiom that only contains variables from X, then mapping it with R is the same value as mapping it with R of X. Okay, but by assumption, R of X is a reduction operator for this Px over Sx, so it must map any axiom in this Px side to 0. Okay, and similarly for the Q axioms. And finally, this commutativity follows from the following chain of operations, basically. So first, given R of X xi times m, this basically decomposes into R of X times xi, and then times the projection of m to the x variables times ry times the projection of m to the y variables. Okay. Well, this R of X has this commutativity property. So this part becomes this. So R of X of xi times R of X of mx. Okay. But on the other hand, this side, this ry has idempotency. So we have R of y of my. Okay. So now, by linearity, this we can combine these sides now to the R of xi, R of X of mx, and ry of m of y. Okay. And now, by definition, this last part here is R of m. Okay. So we get this commutativity kind of property. That's really the whole proof of the disjunction property. Okay.
And I guess the one difference you have compared to, or I guess the way Razborov builds his operators, that he always gets this, I guess, but this idempotency is somehow usually not needed, right? But you actually needed it because in order to make this latest argument to work, for instance, you needed it to apply R twice to the Y part, for instance.
Yes.
And then
Yes.
if things would have gone out of control if things changed the second time you applied R.
Yeah.
And I guess I'm thinking I can't think of an R operator that wouldn't satisfy this, but somehow we don't have it as a condition, I think, usually because we don't need it.
Yeah. I think yes. Razborov, I think in the Pigeonhole paper, he gets an operator that has this property and it's actually used at some point, but I'm not 100% sure about this.
Mm-hmm.
But okay. But yes, for soundness, it's definitely not needed, and thus for lower bounds it is not necessarily needed. Okay. Okay. So the proof search, just quickly mention something about this. So the basic idea is to generate a basis for this subspace of all polynomials provable from Q over S, and also carry along proofs for the basis elements. A basis that has the following nice property that any element in the basis has a distinct leading monomial. Then checking whether some element is provable is just simply a task of reducing this P with respect to the basis, given basis, because you always have when they have distinct leading monomials, you always, there's no real choice of what to use to basically reduce it further. Okay, and if you reach 0, then you know that P is provable. And the algorithm is just it's a modification of the like Edmonds and Imbagliazzo. So basically you start with your axioms and want to build this basis. So at each step you take some polynomial away from this set I and look at its leading monomial. If the leading monomial is inside is one of the leading monomials of B, then you take one element of the B and reduce this polynomial with this Q and obtain a new P, and for which you again look at basically until the leading monomial of the P is not already in B. And if P is non-zero, then you add it to B. And if it is a polynomial containing only monomials from S, then add any lift of this P to the initial set. Okay. So this okay. So then it's a lemma to prove that basically yes, this is indeed a basis for the set of all provable polynomials. And this this proof search algorithm always holds in polynomially many, polynomially many steps in the size of Q and the size of S. But if there's but with rational surreals, there's in these steps, there's real potential of the coefficient load that you basically might end up doubling the maximum coefficients in I after each of these loops, and then you end up with easily with doubly exponential coefficients. Okay. And just to mention quickly this counterexample for Q that I mentioned in the first half, that has in some sense small proofs, so of degree 2 and small number of monomials, but for which any proof basically must be of exponential bit complexity if one writes the coefficients with the reduced fractions in binary, basically. So the counterexample is as follows. So basically you have 2 times n squared variables and in many copies of basic, kind of a basic knapsack constraint. So the constraints are here so there's this repeated squaring that's inherent here, that basically this last constraint here by itself is unsatisfiable over the Boolean values, but this needs like a degree n to refute in polynomial calculus. So these two.
So do we also have Boolean axioms
this,
here hidden somewhere?
Have twofold purpose here. Basically, they found the degree needed to refute this set, but this repeated squaring here forces the coefficients to blow up.
But should we think of these variables as Boolean?
Yes. So these.
So they're also x squared minus x axioms.
Yes. Yes.
Okay. Good.
Okay. And this is a slight modification of an example given by Rakavendra and Weitz to prove they showed that there's a set of constraints that and a target polynomial that target polynomial has always a degree 2 sums of squares proofs of non-negativity, but until you go to square root of n degree, you'll have basically doubly exponential coefficients. So this is like an building up on that example. It's polynomial calculus. Okay. So let's see some of the details for sums of squares then. So again, about this semantic argument. So just a recap. We call a epsilon pseudo expectation this kind of linear functional that maps these axioms epsilon goes to 0. And the idea is to prove this soundness and completeness theorems. So soundness is just as simply as follows. So assuming you'd have this refutation with coefficients here bounded by a suitable value. Then you'd have that all of these lifts get a value of 1 over size of q plus n, and similar for this complementarity values, complementarity axioms. And so you get that all of this part here gets a value less than 1 in absolute value.
So,
Okay.
Tuomas, just a
by
question.
applying e to the both sides of this, you get a trivial contradiction of 1 minus 1 is strictly larger than -1. Okay.
A question.
Yes.
Is it so? I realize now I missed the previous slide. So is it the same thing here as with the R operator, that you're actually the pseudo expectation exists for all degrees, or is it degree bounded? Because I mean, usually these pseudo expectations for SOS go up to some degree D or something, but here,
Yes.
And how is it here? Do you do them for arbitrary degree, or?
So again, it's for proofs over a set of monomials. So so again, a slight generalization of this notion of a degree bounded SOS proof of looking at proofs that use only some monomials from some fixed set of monomials, basically.
Okay, I see.
Okay. And the completeness proof is an application of a basically hyperplane separation theorem. So assuming that you don't have an R-bounded refutation of Q over S, then consider the two following sets. So all the polynomials in R of S squared that are squares modulo multilinearization. Okay, and then this so these kinds of polynomials -1 plus some lifts of the axioms plus some lifts of the complementarity axioms, where these coefficients are not too large. So with this assumption that there's no R-bounded refutation of Q over S, these two sets are disjoint. Okay, and moreover, A is a convex cone in the space R S squared, and B is a convex set there. So by a hyperplane separation theorem, so a variety of hyperplane separation theorem for convex cones versus convex sets, you get a non-trivial linear functional, basically a hyperplane going through the origin. So you get a linear functional that maps anything in A to non-negative value and anything in B to a non-positive value. Okay. So first we need to argue that this kind of E gets a strictly positive value for the constant polynomial 1. And this follows from a property that the cone of all polynomials that are sums of squares modulo multilinearization have. So they have this, that any monomial here in S squared has provable lower and upper bounds. Okay. And from this it follows, if the constant polynomial 1 would have a value 0, that any monomial from S squared would have also value 0, which is against the assumption about the non-triviality of this linear function. So E is non-negative, and without loss of generality, we can assume that this E1 is actually 1, or by scaling it appropriately. And I would say now it's a easy to see that this E has the desired properties. So so most importantly, these properties that it maps lifts of the axioms to 1 over r close to 0. They follow by because -1 plus minus this r mq is in the set D, and so by assumption they get value. They get a value non-positive value, and then by rearranging you get this this appropriate value. So okay, how much time do I have still?
Well, we're not very formal around here. So
Yeah.
how much time do you want?
No, I think I can. Yeah, okay. So I think this takes maybe 10-15 minutes.
Okay, let's do 10-15 minutes.
Okay. So okay. So now again, the feasible disjunction property is a quite a almost trivial proof, given that we have the right definition at our hands. This bound that we need to carry along here makes it a bit more tricky, but not much. Okay. So again, just a reminder, so that the idea is that assuming that you wouldn't have these refutations, and you'd have these pseudo expectations for these sets, and you could combine these to a new linear function that works against the given refutation. So it has these properties. So let's go quickly through this. Okay. So again, let's start with this second. So any square gets a non-negative value. Well, this is simply as follows. So write this P as a sum of coefficients times the monomials in S, and consider this matrix of this, the values that the E of y gives to these cross terms of these projections of elements from S. Okay. So now, because this E y has this property that it maps any square to a non-negative value, this matrix is positive semi-definite, and so there are some vectors u such that these values can be expressed as a sum of over u's of um times prime. Okay, and thus we have that E of this square of P can be written like so this comes directly from the definition. From this positive semi-definiteness of this matrix, you have that this can be written as with basically omitting this EY part here, and then this can be combined into a EX of some square, and we get a non-negative value because EX satisfies such things. Okay, and the other properties are simple. So it maps 1-to-1 because the components map them 1-to-1. It maps these Boolean axioms to 0 because the components map them to 0. And these axioms maps 1 over r prime close to 0 for two reasons. Because EX maps this part 1 over R prime close to 0, and because EY MY maps this to a value a bit whose absolute value is at most 1. Okay. So it's again basically the whole proof of the feasible disjunction property. Okay. So for the proof search, I'm just gonna say some things quickly. So we have bound the coefficients in the lifts of the axioms, but we need to bound the coefficients in the sum of squares part also. But this follows from a following lemma, which is a slight modification of a theorem or modification of a special case of a theorem of Rakavendra and White's. Okay, so if one has this some p that is a sum of squares modulo multilinearization, then one can always write it as equality modulo multilinearization of some PSD matrix times this. So this is the vector of all monomials in S basically. Okay, but one can actually bound these entries in C by a polynomial whose so that the entries can be represented by polynomial bits, number of bits that's polynomial in the size of S and logarithm of the coefficients in P. Okay. So using this lemma, this gives us our initial ellipsoid, and so the proof search, as stated, can be formalized as a semi-definite program of size polynomial in the encoding of the given Q's and the size of S. We get this initial ellipsoid from the previous lemma, and the full dimensionality we can obtain by a standard trick of fuzzying the many equality constraints in the SDP to these kinds of inequality constraints for a suitably small epsilon. And this gives then a fuzzy solution of the form P plus some linear combination of the monomials in S squared. Okay. And okay, and this then can be again using the fact that one has provable upper and lower bounds for any monomial in S squared can be corrected into a solution of the form of this form. Let's say like a solution up to an additive error. Okay, so I think that was everything I wanted to tell. Are there any questions at this point?
So I guess we had a bunch of questions already during the presentation, but I don't know if there's anything left to ask about. Maybe final. I mean, I guess did you have this slide that one tends to have at the end of presentations, or the one thing I'm asking, like, where do we go from here? Future directions. Is this okay? Now you have what you wanted, or is it like, is there a next step? Something you'd want to do, or something you want to use this for, or extend, or I don't know.
Yes, so we had this in the first part basically, but
right. Yes, sorry.
yeah, but yeah, so so this is yeah. So I guess my favorite question related to this is the last one, whether one can actually prove a or maybe even disprove feasible disjunction property using semantic arguments. I'm not quite sure about this.
And when you say monotone feasible interpolation, then you think about then you're thinking about dumping proofs to monotone Boolean circuits.
Yes.
Because there is also, I mean, there is some wait, so I should know this, but I don't. So for polynomial calculus, there is some kind of interpolation to, what is it? What are these called? Like to span programs or something like that? So like Pudlak and someone, or?
Yes, so
it seems like you can also play around with your target language a bit somehow, or target domain.
Yes. So yes, it's Skull and Pudlak, I think. They have this interpolation with respect to yes, something like polynomial programs or something like this. But that's also for a degree bounded case. So it's not with respect to the size of the proof, but with a bound on degree, one can transform it to some kind of a program. Yes. Yeah.
I see.
Yeah.
Fair enough. Any other questions before we thank Thomas again for this Friday afternoon entertainment? So thanks so much again, Thomas, from all of us. And I think this is the official end of the seminar. Thank you so much.
Okay, thank you.